I think everyone will agree we've got a great lineup of lectures today. There's something here for everybody, I think. And I'd like to take the opportunity to say thank you to Sarah and to David for putting together such a great collection of lectures for us.
Our next lecture is Pairing for 5G, Hardened Connectivity. It's given by Vanesa Diaz, who's a Market Development Manager at EMEA, Corning Optical Communication, responsible for developing competitive response for the EMEA market and specialising in fibre access networks for mobile and MSO operators. Before joining Corning in 2010, Vanessa worked as a research and development engineer for RIMSA, an antenna and RF device manufacturer, as a network supervisor for Vodafone Spain. So, a warm welcome to Vanessa.
I thought something to start with. Actually, I just saw these two machines earlier, and I thought that this is the perfect example of machine-to-machine communication. This is very framed on what I'm bringing today to this speaking slot. I want to talk about my favorite topic ever, is 5G, because it's promising to bring the future, and because it is relevant for the cable industry. So I thought that it was a good idea to just, walk around what's going on out there on this matter. So starting from the beginning, I think that the first thing to do is to congratulate the cable industry, because over the last 10 years, these are the statistics released in March this year from IHS, is doing fantastically well. So we're talking about last year a revenue around 23.4 billion euros alone. So remarkable achievements, and still sustained by the three triple play services offered by this type of operators. So internet, telephony, and television. What we see is that there is a change in the consumer behavior. We can see it already here, because the internet is actually growing at a much faster pace than the television and telephony, which is on the client. And if we look even a bit deeper on what's going on the TV section or market, we see that the users, ourselves, we are actually more prone into this TV that we just choose whenever. So we're talking about this video on demand. So Netflix, HBO. I personally became a massive fan of Netflix. So probably I shouldn't have said that. Right. So this is showing where we're going. We want to consume the data when we want it. And the next thing that is now coming to the mix is where we want it. Because users have started to now view broadband technology in an agnostic matter. That means that I really don't care whether with my phone or with my laptop I'm connecting to the antenna outside, or if I'm connected to a Wi-Fi spot. Actually, there are very interesting information or data points out there, and this is one of them. So what we see is that by 2013, the Americans that had a smartphone but no home broadband was around 8%, and that increased to 13%. So this is a very interesting point, that it shows where we're going. The other thing that's happening is that this was enabled by the mobile operators in 2010 when the smartphone was introduced, and then 4G technology started to really deliver high data rates. That's when the mobile industry or the mobile operators started to be able to compete on delivering high data rates in the telecom industry. This completely reshaped everything because, as I was saying earlier, it was no longer about providing this triple play, television, internet, and the voice. We also had to provide that on the go. So we're talking about this famous quadruple play. Actually, we're seeing in the industry a lot of operators that have been, acquiring their counterparts to be able to provide all these services simultaneously. Liberty Global and Ziggo in the Netherlands is a great example of that. So looking at where we're going, the cable industry is actually pretty well positioned, at least for now, because although we are generating a lot of data from our mobile phones, the reality is that that data is being captured most of the time by a Wi-Fi point, not the mobile network. So that's what we're seeing here. And what's behind those Wi-Fi points in 72% of the cases in this analysis is actually a cable operator. So the cable industry is making the right choice where they're deploying fiber deeper, and deeper, and it's the right direction to go, considering that this is going to change now, and the amount of data that is going to be carried by the mobile networks is going to increase. So the cable industry has to be ready to be able to do this as well, offering this quadruple play. So this is when we go into what's next. 5G is going to be the fifth industrial revolution. This is a note that I read like a couple of weeks ago from the AT&T Chief Technology Officer. I thought it was pretty much setting the scenario of what is coming. We are at the dawn of something new that will define the next decade and generation of connectivity. Much like 4G introduced the world to the gig economy, mobile 5G will jumpstart the next wave of unforeseen innovation. Unforeseen innovation, so that's why I'm well up for the future. So that's the reason why 5G is one of my most favorite topics ever. So 5G is promising a lot of things. It's promising to deliver a lot of services, and they will require pretty much three ingredients. They will be using some, two, or only one, or the three of them, of these ingredients, meaning 5G will enable enhanced broadband. This is kind of like a natural evolution of the technologies, the mobile technologies, because that is what 3G and 4G have been doing. They've been giving us more and more bandwidth. 5G is going to take it to the next level. But as I said, it's kind of like a natural progression. 5G is also bringing two new things that will revolutionize everything. One is the IoT that we heard before, the capabilities that it has. We're talking about billions of tiny devices that will be able to communicate with the network and send tons of information. And the last but not least piece of innovation that 5G will bring is this machine-to-machine communication that it will take place in real time. And that is going to allow these cars to be driven remotely or maybe automatically. We might not need to go back to the factories to operate the machines there. We can do it from a different location and so on. So this is a fantastic world of opportunities that will open, but things will have to change at the network level. So this slide is just to show that actually fixed and mobile networks, whether it's a carrier or an HFC network, they are actually not very different, because at the end they are only wireless at the edge. We always have, in both networks, we have a core that carries the chunk of the information. We have a metro, and then we also have an access part. And the only difference is that when I talk about a mobile network, I call that a radio access network, RAN. So you're going to hear me now using that term a lot for the rest of the presentation. So the same way that when I'm in my home, I connect to an antenna, the antenna of my router, the same way I connect to an antenna when I am connecting to a mobile network. So not much difference there. Difference are, well, both transmission mediums are shared, meaning everyone in my family connects to the same modem. There is not that much difficulty there because the space is quite limited, it's small, so there are not a lot of problems on sharing. There are no capacity constraints. If I go to the mobile environment, though, it's a completely different story because I have a massive antenna maybe on the top of a building, and a lot of people, we're talking about hundreds of people, connecting to that same antenna and using those same resources. So what we need to do here, or what the cellular or mobile networks do, is they assign to an area an antenna, and then they create another area. That's what is called a cell. They create another cell with another antenna. And what they do is they get these two antennas to speak at different frequencies. It's like different languages. This way, the antennas do not interfere with each other. So you start to see here where the story is going. Mobile networks is a lot about frequencies. So back to the initial question, what does 5G need to materialize? The first thing that it needs is frequencies. This is how the 5G standard looks like. You know that it's still a work in progress, meaning we're defining bit by bit all the different parts of this protocol until it's completed by 2020. And it's estimated that it will be in 2021 when the biggest CapEx investment will take place worldwide. You also can see here, I think it's quite interesting to see that they've been implementing all these different pillars of 5G gradually. So now we're capable of delivering high data rates, and that's the reason why when we hear about 5G trials around the world, what we see, what they brag about, is the super high data rates that they can deliver. What's next is a solid implementation of the IoT. And the last one, probably because it's the most difficult to implement, we will see this machine-to-machine, super extreme, fast, low latency communication at the very end of the road. Right, so what you're seeing here at the bottom, it's what the different countries are doing in 5G in terms of frequencies. They are releasing or they are embracing different parts of the spectrum, and they are doing so depending on what they are thinking what part of 5G they will implement, what business case they have in mind. And I'm going to explain this a little bit more in detail. Right, so what we're seeing here is the whole frequency spectrum. And here at the bottom, I'm measuring the amount of data that I can transmit. It's an approximation. What you can see here is that the higher up I go in the frequency spectrum, the more data I can transmit. If I make an analogy, it's like if I speak super fast, I can actually transmit a lot more information in shorter time. So it's kind of like that. So you would think, well, why then all these technologies, 4G, 3G, 2G, live here at the bottom? The reason is because it's easier to implement, or it was easier to implement all the hardware needed to operate a mobile network using these low frequencies here. Actually, it was the military world, the one that entered first at these higher frequencies. So how does the frequency spectrum work? Okay, another reason as well why these technologies are living here. This section at the bottom is called sub-6 gigahertz. These frequencies are extremely robust. That means that they can go through literally solid things. So I don't need line of sight, so I don't need the transceiver and the receiver to see each other. That's why I can actually walk behind a tree or behind a car or a bus, and I still get the signal in my phone from the antenna that is over there. The thing is that there is a relationship between the frequency that the antenna is transmitting and the size of the antenna, and it's inversely proportional. So that means that at these low frequencies here, my antennas are very big. Right, this part of the spectrum, as I said, is very robust. So if you want mobility, if you want to be able to have data rates and move around and still have them, that's where you have to be, at least till now. There is another band. It's called the microwave or centimeter. Technically, it's up to 30 gigahertz. And here what I have is antennas that are slightly smaller. So these one here are those panel antennas, long ones that you see at the top of buildings and towers. Microwave antennas are the little dishes that you can see. Well, little, they would be something like that. They are, these frequencies are quite robust, not as much as this one, so they can tolerate near line of sight, which means if between the transceiver and the receiver there is half of a tree, it still works. And they actually tolerate quite well the rain as well. You know, and So these are the ones that you can see as well in the towers, sending information back to the network. And then last but not least, the famous millimeter wave. Technically, starting from 30 gigahertz. What you can imagine here is, based on what I've been saying to you, I can transmit a lot of data. My antennas are quite petite. The only thing is that my frequencies are a lot more delicate now. So I really, really need to have line of sight. I cannot have anything in between my transceiver and my receiver, otherwise it cracks completely the link. Okay. With this masterclass in frequencies, now we can understand how 5G works. So 5G is going to be the first technology that is going to live beyond these sub-6 gigahertz frequencies. Yes, of course, there is a big important part of the 5G technology that will take place there, and it's something natural. It has to happen, because this is where I have mobility, if you remember. So that's the reason why we see a lot of countries, Japan, well, everyone pretty much everyone in the world is signing up for these frequencies. I think it was just yesterday when Italy finished their auction, and then I think Spain is already done. I think that the only thing that is remaining here is this band here. It's quite important. It's actually slightly below. They are reopening frequencies that haven't been used in a while. They are reopening for 5G. Right, there is another band. And this is why I've been insisting all this time on this 30 gigahertz. Because for some reason in the industry, we hear all this time this frequency is called millimeter, although technically they belong to the centimeter part of the spectrum. Regardless, what we see is that most countries as well are signing up for these frequencies here. Because you lose mobility there, but you can provide super, super high data rates. And that's the reason why. And then we have some other frequencies even higher up. So as you can see, 5G is a protocol that it lives everywhere. Now, I said at the beginning that the operators were embracing the frequencies depending on the business cases or the services that they wanted to deliver. And that's what I'm trying to represent here. So fixed wireless access, you know, that is pretty much like using my phone as a modem. That's what fixed wireless access is. And it's becoming super popular in some parts of the world. For example, in North America, we see that 95% of the development efforts towards 5G is going into that technology because there is a strong business case for them. It makes more sense, and I'll explain you later why, to get to an area, put a big antenna there, or maybe small cell antennas, and then connect all those customers wirelessly using this fixed wireless access connection rather than deploying. But it depends, it varies. Some of the places it doesn't make sense, and it is more reasonable to go with the cable, a physical fiber cable, and keep connecting the customers with a drop, so they get fiber to the home. So if we look at how the market looks like, this is a quite basic estimation from Nokia, but I think it shows, it does the job, and it shows where we're going. There will be a big chunk of services obviously deployed here in these sub-6 gigahertz frequencies, and then all these services that I'm telling you in fixed wireless access as well. Okay, so when we hear about 5G, we talk a lot about coverage area being reduced, densification needed. So really, what happens, because it's true, I said to you, that the higher the frequency, the more delicate the signal, so it compromises the reach as well. So it's true that if I go to super high frequencies, I'm going to see that I cannot reach as far as I used to if I was on the sub-6 gigahertz. On the centimeter frequencies, the picture is a little bit, compromises the coverage. It's not the end of the world. And then, of course, if I deploy 5G radios on the sub-6 gigahertz, the coverage will be quite similar. Why is this important? Because preparing my radio access network for 5G, what I'm going to have to do is at least address somehow this slightly reduced coverage. And to do so, there are two fundamental approaches, the fancy and the traditional. The fancy is for those operators who have the luxury of a quite dense RAN network, meaning I have enough density of towers and top of buildings with my antennas. So if I if I add there my 5G radios, I get to cover the same areas as before. That's fantastic, okay. So these guys can overcome this problem by using massive MIMO and beamforming. But for those other operators who don't have that very nice density of cells, they have to go to the traditional approach of densifying even further, whether with macros or with small cells. So I'm going to show you here what massive MIMO and beamforming is. Massive MIMO, this is multiple input, multiple output. This means that I'm going to have an antenna that is made by sub-antennas. 16, 32, there are actually several variations here. As you can imagine, if I'm going to stack so many antennas together, the antennas have to be small. That's the reason why this solution, it makes sense on higher parts of the frequency spectrum. If I have these sub-antennas, then I can create sub-lobes, or sub-coverage spots. So I can point at very specific parts around myself, or around the antenna. And then beamforming means that I make these antennas intelligent, and so I can literally shift where I'm pointing at, depending on the demand, which area is now struggling with capacity, I go there. So that is what massive MIMO and beamforming is. And as I said to you, this is the fancy way of preparing for 5G. The traditional way, for those operators who don't have enough coverage today, is to densify. You can obviously apply this to any part of the spectrum. And it's about adding some cell sites. And you can do that, well, the idea behind that is very simple. If you remember from the beginning, we've been saying that I'm sharing the resources. So if all of us in this room are connected to the same macro, and the macro is exploding and is not having enough for us all to give us bandwidth, then what I need to do is to add another macro cell site, and then basically these guys here and these guys there will connect to this one. So now there are more resources for each of us. The only difficulty of doing this is that if you remember, these two macros have to speak different languages. They have to employ different frequencies. So this might mean more frequencies in the frequency spectrum, and normally means a lot of money, because if you actually Google the last auctions on 5G, you will see we're talking about billions. So the more that you can reutilize the frequencies, the better. That's the reason why the small cells are quite popular to fill holes. What they do is they literally whisper, using the same frequencies as the macro. They whisper in a small area, looking at just a bunch of people. Instead of 100, we might be talking about just dozens of them. And this is, as I said, a very useful approach to save some OpEx there. Right, so we know what we need to prepare for 5G. So how well positioned is UK on this story? If we look at the number of macro cells worldwide, this will give us an idea on the starting point. So whether I have enough density or not, whether I can just place some 5G radios there and then use fancy massive MIMO and fancy beamforming. And looking at this graph, you will think that, well positioned, because you can see here how EMEA and Asia Pacific are the strongest. You know that Asia is well known for being quite ahead of this race on 5G. But the thing is that it's actually not exactly that for the UK. It turns out that Britain is the 54th in the world for 4G coverage, and a typical user can only access 4G barely half of the time, which are no great news. And I even got another piece of information from the National Infrastructure Commission. They said that the UK is held back by poor mobile phone connectivity. They even identify what's called digital deserts in places that should have adequate signal, and they refer specifically to railroads, roads, and city centers. So from here, looks like we're going to have to do a bit of an effort here. We're going to have to go the traditional way, and we're going to need more sites. Right. The other thing that we can do, and it's important to consider, is if we're going to have to install more sites, if we're going to have to connect them, ideally with optical fiber, because it's the real future-proof technology. It's gonna be the only one really that will cope with what 5G is going to throw in terms of data and whatever comes next. Because 5G is there and 6G is the next one to come. So if you're gonna have to deploy the fiber, ideally you wanna do it right. And by doing it right, I mean considering, for example, going into what is called centralized RAN. So what you're looking at is what we have today, a distributed RAN. This means that the two machines that you need, because the antennas are passive, so the two actives that you need for an antenna, for a cell site to operate, they are co-located in the same cell site. This is the remote radio head. This is like the ears and the mouth, and the baseband unit. This is the brain. The brain is the one that communicates with the core of the network and communicates with other baseband units nearby. Because you remember, I'm moving. That means that I'm connected to one cell, and then when I'm moving to the other one, the first cell has to let the other one know, hey, Vanesa's going over there, get here. Right. So that's the kind of communication that it takes place between them. This link that connects this machine back to the network is a backhaul link. And because it's not particularly demanding in terms of bandwidth or latency, it can actually be implemented with anything, optical, fiber, microwave, copper. But there is another approach, it's a centralized architecture, and it makes a lot of sense to go into this. I'll explain you in a minute why. And what I do here is to get all the baseband units together in a massive machine-to-machine party somewhere. And what I do is I extend the initial backhaul link. The link that it was initially taking place here at the cell site, I'm making it now very long. So what I'm seeing is the signal that they were using to communicate. I'm seeing a different protocol, and I call it differently. This protocol is quite rudimentary because it wasn't designed for long distances. It was designed to be just there. So that's why it's quite inefficient. It just digitalized the signal, even maps the noise. So in the same situation as before, it basically demands or throws a lot of data. That's one of the reasons why you can only or mostly prefer to install or deploy these front haul links using optical fiber. So if you're going to need optical fiber and it's difficult to deploy, why would operators go there? The reason is because there are many reasons. It's pretty much based on the OpEx. It simplifies the run. That means that I'm going to go faster installing now my cell sites because there is literally less hardware that I need to put there. The other thing is that if I have less hardware, I have less maintenance requirements. And then the performance of my mobile network improves massively because I have all these baseband units talking together in this massive party. So I can optimize the resources a lot more, a lot better. And then from an energy reduction point of view, this is actually where this configuration it excels. So those who have implemented it, especially in China, because these guys were in Asia, they are quite ahead on the game. They are the ones that came with this. They report 40 to 50% energy savings. So apparently, it makes sense to go here. How much fiber, though, you need to implement these front haul links? Actually, there are different flavors, many. But I often refer to the two extremes. One extreme is when what I call a fiber-rich approach. And here what I do is I connect every single remote radio head with a dedicated optical fiber. I can need here a lot of fibers, and the reason is because, I can connect simultaneously, I can connect to 3G, 4G from my phone, and still 2G is alive. And the reason is because we don't decommission technologies until they are really, really dead. The only one that it was decommissioned so far, it was 1G. So in the same cell site, I need to have all these technologies coexisting. That I'm going to need as well. That's the reason why you see here, one remote radio head for 2G, two remote radio heads for 3G, because I often have them operating in more than one frequencies. And the same for LTE. This is 4G. I often have a 3-sectorial antenna, which means that to be able to cover the 360 degrees, I have one antenna covering one sector, another antenna, and the last one. So I'm counting. And then this protocol that I'm carrying here, if you remember CPRI, I didn't tell you, but it's not bidirectional. So if you put all these things together, we're talking about a lot of optical fiber. Now, there is another approach. I call it fiber optimized. And this is when you, instead of dedicating one fiber per remote radio head, what you dedicate is one wavelength within the fiber. So this is a quite, fiber optimized approach, because in the same scenario as before, I will be using 2 optical fibers only. So back to the story on the C run. Regardless on how I implement it, although I do get an idea of where I'm hoping that where I'm going. So we see that we need optical fiber. Why would I go into the hassle, right? Where are the real value of C run? So we said that it was scoring from 4 different angles: the site expenses, the maintenance, the energy consumption, and the performance enhancement. Not everyone in the world is doing it, and the reason is because depending on the area or the region of the world, you will see more or less value on all 4 aspects. So for example, in places where the energy is not too expensive, they might not see that much value on this or much, yeah. Depending on the maintenance protocol as well, it varies. That's one of the reasons. And the other one is because we said that it needs fiber availability. So if fiber is not there, it's difficult to make the business case for a C-RAN architecture to fly. But still, this architecture makes a lot of sense for the future, for 5G, because of all the things that I explained before. So that's the reason why Asia, for example, they came with this as they were deploying optical fiber. They had loads of it, so they could go for a super fiber-rich approach with a centralized RAN. US is doing exactly the same. They are having to deploy new sites, and that's the reason why, well, I'm going to use fiber. If I'm going to use fiber, I'm going to do it right, and I'm going to get a network that is future-proof. It's really 5G ready. It's going to save me a lot of energy. And then Europe here, we're still deciding whether this makes sense or not for us. So far, the approach seems to be more in the direction of multiplexing on the same fiber. Now, the thing is now here, so I've just explained to you that whenever you have to deploy fiber, which is linked to whenever you need to densify the network, it makes sense to get it right. So this is the reason why we see 2 radical approaches between North America and Europe in this matter. So what we see is that North America, the majority of sites there, of cell sites, are connected with optical fiber already, but because they are still needing more cells, they are creating them and they are connecting them with optical fiber. EMEA, on the other hand, it has a very great densification, but most of these sites are still connected with microwave solutions. So fiber is going to be necessary in the future to carry all the data generated by 5G. So at the end, you have 2 scenarios, both needing optical fiber regardless. And then we stick to this approach because this is the one that I think UK has to follow as well. And this is what takes me to the next part of the presentation. We're going to have to deploy more fiber here. This is the right time, therefore, for convergence. Convergence is an idea that it was coined back in 2004. There even was an organization that wanted to promote it and so on. And it didn't work because it wasn't the right time back then. What is different today is that for the first time, because of what we saw earlier, this need to offer this quadruple play, more and more operators now own both networks. And if both networks now see the need for optical fiber, we've seen it, so in fixed, we see operators over-provisioning, deploying PON architectures with a lot of extra fibers with the idea in mind of connecting or offering point-to-point connections in the future. In mobile networks, we've seen if you want to go to a C-RAN approach, use optical fiber. If you want to carry all the data, you need 5G. You need optical fiber as well. So if you're going to make a hole in the ground, it makes more sense, considering how expensive it is to dig that hole, to provision from day one for all these services that I'm going to deliver. And that's why the convergence idea, fixed mobile network convergence, finally started to fly. There are many ways to implement convergence, and I'm going to leave aside the ones that work on the actives, and I'm going to focus on the passives, because that's where we, Corning, can help. So what you're looking at is a simplification of how a convergence that is taking place at the infrastructure level looks like. What I have here is what I call all my potential clients, meaning I have my residential, my business that I want to connect with optical fiber, my cell sites, and my DAS. And I have some central office, I don't know how to call this, that is a hybrid where I have basically all the transmitters for all these services. So what I do in a infrastructural convergence, I pretty much use the same cable, the same closure, the same network access point to carry all these services to the end. And this is where hardened connectivity can help. Because if we think about a scenario where we're going to have to deploy fiber and we're going to have to deploy a lot of it, this is when this type of technology can help. A solution, you know that when it comes to deploy fiber, you have two radical approaches. One is a fully spliced solution. That means that you need the splicing machines, the heavy and expensive splicing machines, to be carried to the places and used by well-trained installers that know how to make the fusion of the two fibers. On the other hand, you have connectors and a whole myriad of solutions around those connectors that are called hardened. They are protected. So allow you to, instead of having to splice, allow you to literally plug and then it's done. So as I was saying earlier, when you have this approach, when you need to go really fast, when you need to deploy a network really fast, this is when this type of solutions start to make a lot of sense, and the reason why they are extremely popular, well, in Spain, here they are quite popular as well, in North America, and so on. They go extremely fast because you create connections in a lot less time. The size of the installer teams that you need are a lot smaller as well. And there is a lot more shorter time to revenue because you connect the customers quite straightforward. It can also be done by unskilled technicians. Yes, you might have them trained today. Yes, you might have the splicing machines today, but if you're going to go fast, you're going to lack both. So this can be done by anyone, almost just join, plug and play. And it can be handled like copper. And then finally, the quality. These pieces are sealed. They come from the plant with an IP68 isolation. That means that no tough environment can actually disturb them. And that's what allows the network to be extremely reliable from the first day that you install them and so on. So, I'm sure that you're already wondering, well, I'm sure that this is a little bit more expensive. Yes, it is. But that's the reason why when you look at this type of solutions, you need to look at the overall picture. Because, and that's what I'm trying to represent here, I'm comparing a fully spliced solution with a hardened, or it's called also pre-connectorized box. And what I have here is, I'm representing with a color-coded symbols. So green will mean quite affordable, and then red will be a bit more expensive. So on day one, the material for a fully spliced solution is cheaper. That's agreed. While for a hardened solution, it's hardened on the material. Obviously, the installation is, is supposed to be, well, we're assuming here that it's kind of like the same. But on day two and onwards, as you start connecting the customers themselves, or whatever, and when I say customer, I'm referring to anything, right? I'm referring to a small cell, perhaps, or any other kind of services I have out there. The material for a fully spliced box is cheap, but the installation is very expensive because I need that splicing machine, I need that trained technician, so time, complexity, that means a lot of money. While here, on the other hand, with a solution that is plug and play, you can imagine connecting a customer is literally sending someone with a drop cable, plug it on the terminal, plug it on the customer, and off you go. So that's why when all the manufacturers that work with this type of solution always present or make this analysis on the total cost of ownership. And that's what you're looking at here. These are the total installation costs of these two solutions compared. And what you can see is that, yes, we do start from obviously a slightly more expensive scenario, but as you start connecting small cells or customers, that's when the hardened solution starts to become a lot more affordable. Also, this enables a pay-as-you-grow approach. That means that you can wait for the customers to connect when they are ready. it is also extremely good when you want to have very clear demarcation points. I'll explain you in a minute. At the core of these hardened solutions, there are two siblings. The OptiTap, that is not only ours because we have licensed this little fella to other vendors. The OptiTap is a single fiber connector, and its sibling is called OptiTip, and it has a multi-fiber, it's like an MTP multi-fiber connector, but with a hardened shell to protect it. With these two siblings, we've actually built a whole set of solutions. This is just a glimpse of what this industry can do. And so you have different form factors of this solution depending on your needs. So for example, this is a box that it allows you to do a lot of configurations within, but it's perhaps in some scenarios might be slightly too big, so you might want to go to something a lot smaller like this one. But it comes from the plant looking like this, so you have a tail that connects to the cabinet, and then from this female OptiTaps you will connect the drop customers, the drop cables that connect the customer itself, and so on. So this is another solution that I'll talk to you in a minute. Now, as you can imagine, so this, for example, the multiport that it goes at the very end where you could connect as well the customers there. I was saying to you before, this is extremely useful when you need very clear demarcation points. So imagine that you are, I don't know, you need for whichever the reason to make very clear where your network finishes and someone else's starts. This is extremely useful as well. So based on this technology, we designed a solution, and this is just an example, to answer the requirement of an operator in North America. You might have come across the news, where Verizon was asking for a solution that would allow them to do convergence. So Verizon was in a need of deploying new cells, macro and small. They wanted to do it right. Let's do centralized RAN. And they wanted to do it so right as well that they wanted to be able to provision with the same network to any of their customers. And here I'm talking again about small cells and FTTH customers and even dark fiber. So they wanted something fast, they wanted something off the shelf, and this is what we put together using all these hardened solutions, well, some of them. So what you see here is a new closure that we designed for them that is as well plug and play, so you can see it at the bottom. And it's very light, it's quite condensed or quite, very small form factor. There we go. And then what you can see here is that we're using one of our solutions. It's called FlexNAP, and it replaces the cable and a closure itself, because you have this called tethers where you can have connect to a terminal, a multi-port terminal, from which you will have all these different services provisioned. And then the beauty of this solution is 10 years old now, is that it's extremely fast. It's the fastest way to deploy an FTTH network ever. Actually, the way that this comes, you do have to measure a little bit beforehand because this comes all designed from the plant. But then when you get to the time to deploy it, it comes in a big reel and you literally unroll it, and then either you hang it on a pole or you just put it right on the ground. And there we go. At the end, we had this system, it looks very simple, but there is a lot of complexity behind because we are playing with the two siblings here. We're playing with the OptiTips and the OptiTap to be able to allow for different configurations. I could actually talk about this for a long time. I just wanted to show you what hardened solutions can do today. And this is actually how, sorry, I forgot that I had this. This is how this particular hardened solution looks like. It comes, as I said, in massive reels. Yes. Yeah, we came into the end. So just to conclude, we came here to talk about how the industry is going into this quadruple play. So we need to be able to offer all these services, triple play on the go. And then we are seeing that with the advent of 5G is becoming a lot more critical than ever before. With convergence, fixed mobile convergence, becoming a very, very reasonable approach. So there is a myriad of solutions out there to materialize this, to get ready for this unforeseen innovation. But what we firmly believe is that when the time comes, we need to deploy fast and embrace all these fancy, alternatives, architectures, and so on, a hardened solution can actually make a massive difference. So that's it. See, there we go. Sorry, thank you. It was a little bit longer.